Today we're going to talk about, last time we started talking, actually I should also mention, the tutorials, the submissions are all in. We're hoping to get you feedback on that by Friday. So I will try to go through all those by Friday, and then just, again, it's just like it's a sentence of input. It's going to be a sentence of feedback too. Oftentimes, falling into certain categories too. So a lot of neural network projects, I have a similar comment about a lot of them. But we'll get that back ideally by Friday, so then you'll have, can ignore it over break and just think about it, and then when you get back, you'll have some time to work on it again. I think that's all. There's and again, homework 3 is due Wednesday, but with late days extendable to Friday, and so hopefully that's all going well. Any questions about either of those two topics, the homework or the tutorial? Okay. All right, so this time we're going to keep going with nonlinear modeling. And actually, this is a little bit of an odd lecture, just organizationally, and sort of the slides get a little bit off of this. So I'm both going from the slides from nonlinear modeling here, as well as a short bit of slides on model evaluation in machine learning. But I updated the slides on nonlinear modeling, too, to add this one section on kernels, which I wanted to talk about. So just be aware that get the latest version of the slides here, and we're also updating the notes kind of slower than real time, sadly, but I think fortunately spring break is coming soon, and that's a good time to sit down and write some notes, so I'll hopefully catch up with that by then. All right, so when we left last time, I kind of introduced these notions of nonlinear, kind of nonlinear modeling, but not really nonlinear modeling. It's still linear regression, but capturing nonlinear functions of the data through the use of nonlinear features. And that was kind of the crux of how we actually go about, at least with simple machine learning models, capturing nonlinear behavior. So I want to spend a little time right now, and this is going to be actually probably the most kind of mathematical notation, or at least kind of most abstract mathematical notation in the whole course, talking about general nonlinear features we can use. And there's really two types of nonlinear features that are very common here. One is polynomial features, which we talked about a little bit before. We're going to talk about the general case now when you have multiple dimensions in your raw input. And then I want to talk about radial basis functions for nonlinear features as well. It's a common type you'll see, and you should know what those are at a high level. Now, chances are you will not go about, in most machine learning and most data science problems, you will not go about designing your own nonlinear features. It's something you can try, certainly, but not the best way to get the quickest good behavior. Typically, you'll just use some nonlinear model directly, oftentimes with a method based upon kernels, or based upon a different nonlinear model like a boosted decision tree or something like that. But it's good to at least, and we're not going to spend too much time on this here because I don't want to belabor the point, but it's good to at least know what some of the basic types of nonlinear features are that you can create with data, to kind of get a sense of how these models work when you apply something like kernels. Because actually kernels are very related to these explicit nonlinear features. They just do it kind of in an implicit way. And last, we'll just very briefly highlight the extension of all these things to classification. So far I've been talking about them in terms of regression, that fitting that line, or not the line anymore, but that fun shape to peak demand. But the same exact techniques apply to classification. And the nice thing, as you might expect, is that with classification algorithms, you get the same kind of, because our framework treats them in the same way, you have the exact same sort of procedure here. You just basically create nonlinear versions of your features for a classification task, and you get nonlinear decision boundaries that separate positive and negative classes. Okay, so let's just jump right into, and then we will end the class, and I hope we'll be able to get to all of it with a separate set of slides, which actually are the slides that are linked to this lecture on the web page. But those are a much shorter set on evaluating methods for machine learning, or models in machine learning. Okay, let's jump in. Okay, so the one thing I'm going to note here, so previously we talked about polynomials. They're kind of obvious when there's a single raw input, like temperature. The polynomials are kind of obvious, right? It's temperature, temperature squared, temperature cubed, however many you want to go. Also the constant term, which is temperature to the 0. But to define them for a little bit more raw input. So remember our classification task, for example, we had the mean concave area or mean number of concave points, and we had the area of these things. We use more than just one raw input feature, and so the question is, how do you extend things like polynomials or define other nonlinear functions for more broad, richer sets of inputs to your algorithm? So I'm going to actually here talk about a little bit different set of notations here. I'm going to actually define xi and phi I to be two separate things. So from now on, or at least just for, sorry, not from now on, but just for this section, phi is going to denote our set of features, whereas x will denote just the raw input. Okay, so by that what I mean is that in the example before, x would have been just the high temperature, and phi would have been the vector of the temperature squared, the temperature, and the constant term. Okay, this is a pretty common notation in machine learning to use phi for to denote sort of sets of features in general, and I'm going to use that just here, but you have to be aware of this notational thing. Okay, all right. So the first thing, and again, this is, if you don't understand the details here or the exact math I'm writing down, please don't worry. The high-level ideas are what's important here, and I'll try to emphasize those as well. Okay, so let's talk about polynomial features for now. So again, x is now our vector in R. I'm saying x is in Rk because we care n is going to be the dimensionality of our feature vector, not of our raw input. But for, say we have raw inputs that are k-dimensional. Okay, so this is like in the case of that classification task, or rather, we had another regression task, right, where we had two underlying features. One was the high temperature, and one was a flag whether it was a weekday or not. Right, so in that case, there would have been two raw inputs, so k would have been two-dimensional there. So now the question is, when I have raw inputs of more than one dimension, how do I create polynomial features from those things? Okay, because polynomials are a very powerful class of nonlinear feature that you kind of want to be able to express these higher order functions of multiple inputs. So one thing you can do, kind of the most basic thing, is you just take each feature individually and create a set of all the polynomials of it, right? All the individual polynomials of that degree. So you have, x1 to the d down to x1, xk to the d down to xk, and then a single constant term, because you don't need more than one constant term. Those are all the same for everyone. Okay, but the problem here is that this ignores a set of important features here. This ignores things like cross terms, so like x1 times x2 squared times xk. Right, and so in reality, there's a lot more possible nonlinear terms if you want to enumerate all your polynomials than just those. And so we need some way of actually kind of feasibly enumerating all our polynomials. These get pretty big pretty quickly, but you should sort of have a rough sense of how to do this, at least in the lower dimensional cases. All right, so here is sort of the formula for how this actually works. And again, doesn't matter too much here, but it's worth sort of highlighting this thing. Okay, so let me just bring this up. Okay, so if we have some, let's see. Oops, let me actually switch them. I like it better this way. Okay. All right, so if we have some vector, boy. Okay, there we go. X, which is k-dimensional. All right, how do we pick out all possible k-dimensional or d-degree polynomials from there? So one sort of very kind of naive way to write that all, which doesn't really help you implement it. I'll talk about the implementation in a second. But the set of all polynomials we want to capture really is kind of, you can think of it kind of like a set, right? Where the set is the product from I equals 1 to k. That is our total number of input dimensions of xi to the bi, where bi are our various degrees of different polynomials. And this is every possible combination of polynomials here such that the sum from I equals 1 to k of bi is less than or equal to our total degree of our polynomial, right? And that sort of enumerates the set of all possible polynomials. K is it's oh, sorry, that should be k. Yeah, that should be k here. All right, thank you. Now, it isn't too hard to see this, but I'm not going to prove it too much, that the number of those things is k plus d, the degree of the polynomial. Choose k. By the way, it can also be choose d. Those are the same thing. Basically, you can pick. That's just sort of combinatorics that sort of work out. I won't go into why that is actually, but oops, I sort of already gave it. Okay. So this is sort of a nice definition, but it doesn't really help you actually generate the polynomials if you want to do it in code. And so the one thing I'll say is that the easy way to do this, there's some easy ways. There's harder and easier ways to do this in Python. But one of the easy ways to do it is to use this iter tools combinations with replacement, which basically will take the product of d terms from x and then multiply them all together. Okay? So again, you're probably not going to ever write these yourself, but it's important. It is useful to be able to know how to go from sort of raw a definition of polynomials that capture all possible combinations to some actual code that would do it. And fortunately, Python has some nice utilities that let you do that. And in fact, you can also, if you want, this is only polynomials of degree d. If you want everything up to degree d, you actually have to use a double list comprehension, which says for I in the range to d plus 1, and then for the combinations from x to basically select I of those. Okay, so it's a little bit nasty there. And again, I wouldn't encourage anyone to actually do this to create polynomial features, but it's useful to sort of see how you might go about doing these kind of things. We're going to later talk about how one way of doing this kind of in practice with kernels, which lets you do it, but without actually generating these things explicitly. And so here's some code, if you care about it, of doing the same thing, but doing it for entire data matrix X. So this is actually something that's, I'm only putting it here because this is something that people find very hard. If I tell people to take a data matrix X and generate all possible polynomials of that matrix, this ends up being a hard thing. People have a really hard time with this, especially if you can do it for like 2. You just use a for loop, but how do you have a number of for loops equal to the number of inputs you have? And so people find a really hard time with it. So I just want to emphasize that this can be done pretty easily. The way I'm doing it here is just using a reduce operator that multiplies these things together column by column, so I can apply it to each column. And then I just apply the same logic I had before. But again, probably not something you want to do too much, but good to know how it actually can be done in Python, because otherwise this is actually can seem like a pretty hard thing to implement. Okay, so that's actually all I want to say about general polynomial features for now. It's really more just notation than anything else, just saying that what I mean when I say polynomial features of data for some k-dimensional underlying input is I mean all possible multiplications up to degree d of those different features. Okay, and this is the code that if you want to do that, we'll let you create that. Again, not that common to do in practice, but for maybe even low degree polynomials, actually you can do this sometimes, and it can be quite useful. So this is how these things kind of work. Okay, so the other type of basis of nonlinear feature that I want to highlight here are something called radial basis functions. And this is actually, in practice, even more useful. And this one you actually might use in practice sometimes. So I would actually recommend trying this one out as an example. And we'll have some more. I will put some more examples of this in the. Let me put this back. In the notes themselves. But for now, I just wanted to define kind of a notation here and talk about what I mean by this. So, I was about to go back to it. Oh well. Okay. So again, we have this setting here is like the polynomial features. I also want to define, so both the times they're going to have this. This is one type of feature, and this is another type of feature I'm going to talk about. So another very important type of feature are these things called radial basis functions. And what these are an expression of features that themselves are essentially exponentials of distances from that input point, x, to a bunch of centers of what are called centers. So let me actually draw what this looks like. So if I have my input space here, so say I have 2 dimensions, x1 and x2, right? And I have a bunch of points in that space, okay? Now, in this sort of space here, this is just 2-dimensional. These things are just 2-dimensional, right? And so you can't really, I mean, if I have like linear functions in these 2 dimensions, they can only capture linear separators in this space. What I'm going to do in the radial basis function representation is I'm going to take this space and I'm going to plop down some number of centers, I'm calling them. Okay, so I'm going to call this one mu1, or I use superscripts there. Mu1, call this one here mu2, mu3, etc. Mu4, mu5, mu6. Okay, you get the idea. And now, if I have some point here, so now I have some point here, say, this is xi. I'm going to represent this point by looking at the distance from that point to all the other centers. Okay, so I'm going to take this point and just compute distances to each of these things. Look at this distance, this distance, etc., for all the possible distances there. And the feature that is going to be created is just going to be the an exponential, just so that you have distances themselves aren't as useful. It's better to take the exponential because then it has a max of 1 until you scale it at least, and also has a little nicer properties that kind of capture the local aspects of this feature. But basically, I'm going to represent it as my feature is going to be equal to the set of all distances, the exponential of the distances between these two, between this point and all the centers. So basically, going to be the exponential of x minus mu1 over, and I have this term here called sigma, which I'm calling a bandwidth parameter. And then, but we have the feature correspond to all of these things. X minus mu2. Okay, so why is this a useful kind of way of representing the data? Think about the case where you have a lot of these centers, and where this term here is very small. So the bandwidth is very small. Okay, in that case, for the most part, this distance here is going to be, for a reasonable distance, it's going to be big divided by something really small. So it's going to be really big, this thing, and so negative of that thing is going to be really small. So basically, what happens is that those terms are almost 0 for every center except the one that you're really close to. Okay, so for every center, most of these terms are going to be 0, except for the one that you're like right next to. And so in some ways, this kind of feature becomes kind of an encoding of which points you're close to in space, right, in this space. And because we can sort of drop as many of these centers as we want, this can be as rich a representation of our input as we want it to be. We just add more centers. That gives it sort of more points that we can be close to. We can decrease that bandwidth such that we don't overlap with too many of the sensors at once. Okay, so that's the high-level intuition there. Again, if that was seemed a little bit fast or anything, don't worry. I'm just trying to sort of capture the basic ideas here. But this one is actually a pretty useful feature to use in practice, and we'll show some examples of it in a second, kind of what these look like when you actually use radial basis functions for, in our case, a classification problem. But does that make sense what I'm defining there in terms of the definition of the feature? Any questions? Okay, so some important comments here. Radial basis functions, and also things like radial basis function kernels, by the way, which you probably won't encounter these too much. You will encounter RBF kernels for things like support vector machines. Those are very common. You might have encountered these too. I don't know. I think they're actually a pretty useful method. Before you compute this, you need to normalize the columns of X. the different features have to be all normalized, right? And the reason for that is that if you're computing these distances, Euclidean distances, and you have one feature with the range 0 to 0.1 and one feature with the range 0 to 2,000, those are going to be in wildly different ranges, and so you're going to have the distances dominated by the bigger ones, okay? Because the other ones are going to be always very, very close. So just as normalization was really important when we talked about the performance of gradient descent, normalization is also very important when we talk about computing features like radial basis function features. Okay, so whenever you apply like a support vector machine with a radial basis function kernel, you have to make sure to normalize the features first. The second thing is that there are some free choices. There are lots of hyperparameters you can choose in these kernels. So for example, the size, the number and location of the centers are actually a free parameter you have. You can choose whatever you want for the centers and for the number of centers you have. We'll talk about that in a second, but also the bandwidth, the thing you divide by, which basically makes them more narrow or more likely to fall off to 0 quickly or stay at near 1 for a long time. Those things also are the hyperparameters that we have, just like our degree of our polynomial was a hyperparameter. And finally, you can choose those things with cross-validation, though we'll talk in a second about more practical means of doing that too. Okay, so just let me give another example about the high temperature here. So about our example before. So here is the high temperature, x being equal to high temperature. You could choose sort of a uniform distribution of centers. Maybe I choose a bandwidth to be equal to 10, and then our features would turn into this kind of thing like this. I thought I had a slide showing what happened when he did that, but I guess I didn't have that here. Got lost somehow. I'll add those back to the notes so basically, if you do this, it looks very similar to a nonlinear function that you can approximate with the polynomials, but it kind of smoothly interpolates the data and you get a nice nonlinear function. And apologies for that not being there. That will be there in the notes. Okay, the last thing I'll say is if you want generic code that will generate radial basis functions, features for an entire data matrix, an entire matrix of centers, here's the code that does that. So this is the code that will compute pairwise distances between the points x, all the centers mu, and then compute their RBF function between them using this method here. Now, the one thing that sort of you should note is that we're doing this kind of efficiently in that we're computing with a single call square distances between all the inputs and all the centers. And that actually is a very important thing to do. So you can do this very inefficiently by looping over all your points and all your centers, but there are efficient ways to compute distances, and we'll come back to this, I think, actually on a later assignment when we talk about the k-means algorithm also. So just, again, this is kind of going quickly through all this, but just note these things as we go. Okay, so I do want to have a couple quick poll questions, and I think then we'll actually move on from, I have a few more notes about features, but then we'll move on from that, because I don't want to spend too much time on it, but just I want to highlight the main things here. So one of the big issues of features, and I think which is important to understand what they are actually doing, is to understand the complexity of features and the complexity of computing features of the data. So when you talk about nonlinear modeling, one of the things you will sort of need to understand is both sort of how representationally complex they are. So when you use them, how complex of a function are you actually trying to model? So are you doing the 100-degree polynomial or the first-degree polynomial? And secondly, how computationally intensive are they? So are you going to kind of blow through your entire computation just computing these things in the first place, or are you going to be actually able to compute them? So the first question here is talking about if I have an n-dimensional input, m examples, and p centers, what's the complexity of computing the RBF feature for every training example? That is, for all of them. I probably said for all training examples, xi for I equals 1 to m. So again, m is the dimension of the input, m is the number of samples, n is the dimension of the input, and p is the number of RBF features that you are computing. So let's see what people said. All right, so a pretty even split actually between the NMP and N, basically is there an N or an N squared term in there, right? So actually, who wants to take a stab at that? Anyone want to volunteer to argue one way or the other? Who wants to argue for they just ask one way or the other. Who wants to argue for the N squared thing? Who voted for the N squared and wants to give an intuitive explanation of why they think it's there's a quadratic complexity in the underlying dimension? Someone did. I know 71 people said that, so someone has to want to. Or you're just really taking it to heart the fact that it only matters that you input something and not an actual thing you care about. But this can't be just pure chance here. All right. Does anyone want to argue for the single N? Yes. Yeah, we have M samples, that's right. Okay, M samples, yep, I agree. Yep. N example, no. M examples. N dimensions. Yeah. Okay, yes. Okay, so does anyone want to argue the N squared case? You were all convinced by that thoroughly? Okay, well it is right. So you are correct. So basically, the loop here looks like the following, right? It basically is something like this. It's for I in 1 to M, right? That's loop over all my samples, and then for use which letter I should use here for K. I have K, I know meaning something else, but whatever. For K equals 1 to P. So this is now our, over all our centers. I have to compute the distance between my sample and my center. And the way I do that is I just compute, I need to compute, xi minus mu k squared is the main loop there. And that just requires that I compute the element-wise product of each one, which is, this is, of course, going to be order n, because I have to compute, the difference and then just square them. Okay, so this is why it is in fact linear. Your total complexity here is just big O of m, n, and p. So there's no sort of hidden square terms or anything like that. But there is, substantial complexity because you can have a lot of centers, P, you can have a lot of examples, and the dimension can be pretty high. So the product there does sort of start to add up. But it's not hugely bad, right? You're still just producing, a linear number in each of those things. Okay. All right, so just a few more notes here about features in general and the difficulties they face before we move on to kernels and then to just see a few examples. Okay, so the challenge in general, and we're going to talk about how to solve this, sort of, in a second, is that general features here get really complex and really sort of just memory intensive, nothing else, not to mention computation intensive, really quickly. All right. So for example, polynomials, I sort of mentioned a k-dimensional raw input. If I want all degree k polynomials, that's k plus d, choose k, which is, grow for fixed d will grow like d to the k, right? So if you fix your dimensionality and keep increasing the polynomial degree, then that will be exponential essentially in the degree. RBFs are even worse, or they're actually the same, but they're actually a little bit higher even. If you have a k-dimensional raw input, then and you want a uniform grid of d centers over each dimension, then you would have d to the k total features, right? Because you basically have to grid each dimension of your input space, and that'll, of course, the number of features the number of centers you need, i.e., the number of features you have, will grow like d to the k. So while this seems kind of nice from a high level in that we have these sort of generic methods to create general nonlinear classifiers, they really aren't that practical in most settings, right? Because the number of features you create is exponential in your underlying input, which can be, for a lot of machine learning problems, is pretty big. And in both cases, that is a problem both for sort of the memory as well as for the representation of the actual classifier. The latter, the representation might not be that big a deal because we can do other things like regularize to avoid the difficulties there. But it still seems like we're talking about a whole lot of features we're generating here. So we need some other tools to actually make these kind of things practical. And for the most part, there are sort of two techniques you can do for that. First of all, which is what the next two slides are about, there are some ways to kind of reduce the practical number of features you will actually generate for real data science tasks if you still want to go about the case of actually generating explicit features. The second alternative is to use a technique called kernels, which we're going to discuss only very briefly here, but I'm going to highlight the fact that they actually can capture things similar to this with potentially less computation. So let me sort of mention both those two things. Okay, so the sort of lesson of making polynomials practical. Yes, question?
I thought if you look at the code, the centers for each dimension
Yeah.
are the same. So, like for each dimension, you can actually have different centers?
Yes. So in general, in an RBF, if you want kind of like if you really want a full representation of your entire state space, you have no option really but to sort of just grid the entire space. So this is 2 dimensions here. You have to sort of have all possible sets here of things, right? You have no other option but to do all of these. You could be more or less dense in how many you want, but this is basically going to be d to the d squared here. If I have a third dimension now, I have to have one of these for each. I'm bad at drawing in 3 dimensions, but I have one of these for each third dimension, right? So if I want to be able to capture kind of arbitrary functions over d-dimensional or k-dimensional space, I will need, and I want d columns in each one, then I need all d to the k possible centers. I have to make my centers actually sort of the cross product of all possible locations there. If I just do each one individually, like if I just only look at one dimension for the first set of RBF features, I can do that actually. This is actually one of the tricks I can use next time, but it's not even the best way of really doing it. So just know that for kind of the naive thing, which is to cover your entire space, you need an exponential number of centers. Okay. So for polynomials, so I'm going to have just one slide on making these things practical. And these actually are somewhat useful in practice. So these tricks are used. And if you're going to use polynomials or you're going to use RBFs explicitly, you want to use one of these tricks. So for the first of all, don't use the full set of all polynomials for anything but very low dimensional data, like 4-dimensional raw inputs. They just grow, there's just too many of them. They'll grow too fast and they're not going to be actually useful. What you should do instead is form features only where you know the relationships are going to be important. Okay, so this is going to be sort of, this is a type of manual feature engineering here, but it's sort of the reality of things, is that you have to sort of know how to pick your features, or it's just going to be too many. So for example, you might want to have, a quadratic term in your temperature to then multiply by weekday, but you wouldn't have a term where you multiply temperature and humidity together. Because temperature times weekday is sort of this thing. Weekday, remember, is a flag, whether it's weekday or not. That's kind of sensible, right? Sort of saying, what's my quadratic term on the weekdays? That kind of makes sense. But temperature times humidity, if I have humidity as a feature, that doesn't really make sense. I mean, what is that quantity really? I mean, I guess there could be some nonlinear functions there between those two, but maybe not really. And so you want to be sort of discriminating in the features you add. It's also worth mentioning that there's no point in taking higher powers of something like weekday, because weekday is a binary variable. So its square is always equal to itself. And so you're not going to get, there's literally 0 point in doing that one. And so be careful just, when you have things like indicator functions, you never want to, take polynomials in those. You just want to have those times something else. No, doing all this stuff does require some insight into the problem, so I have to sort of know that temperature times weekday is not that relevant. But the reality is that most polynomials are like this. Most polynomial features, if you're going to use them in practice, you have to understand a little bit about the data you're trying to model in order to see how to apply them. And then finally, RBFs. Don't place a grid over your input dimension and have those be your RBF centers. If you have data which is 10-dimensional, your data does not lie in the span of the entire 10-dimensional space. Because the entire span of a 10-dimensional space is so insanely large that nothing in the world would span that whole space. I mean, that's not quite true. But basically, you can never, with any amount of data, come close to covering a 10-dimensional real-valued space. You just don't. What really happens, I mean, just think about how many that would be, right? If you have even 10 grid points in each dimension, that would be 10 to the 10. This is way more data points than you ever actually have. What really happens when you have high-dimensional data is that your data lies in some small subspace of the full data. It's probably a nonlinear subspace. This is why you need nonlinear methods. But your data lies in a small sort of subspace of that. So rather than trying to sort of grid the points evenly, what you should actually do is choose some subset of your data points to be the centers for your RBFs. So use the data points themselves. If you want to be a little bit more, even a little better, you actually can use the k-means algorithm to find good centers for your data. We'll talk about that a little bit later. But basically, the underlying point is, don't pick a uniform grid. Use your data points themselves as centers for your RBFs, and just even sample randomly. That'll do a lot better than trying to grid the whole space. Okay, that's point one. Point two is don't try to pick your bandwidth by cross-validation. This is a really cool trick, actually. It's something, just sort of keep this in mind if you ever hear about it before. But don't pick your bandwidth parameter using cross-validation. Pick it to be the median of distances between the centers. Okay, this is called the median trick sometimes. It's like folklore in machine learning. I can't see it written anywhere, but everyone you sort of does modeling. So this also works, by the way, for RBF kernels in support vector machines. Everyone that sort of does modeling knows this trick. I don't know where it's written down, but it's called the median trick, and it's really useful. There's some theory reasons why that's actually a good amount. It has to do with sort of the spread of the data and things like this, but it's a really simple trick. It's just the median of distances between all the different centers. Pick that as your bandwidth parameter. You basically means that you get some coverage, some crossover between the different RBFs, and it works almost always just as well as picking the best one via cross-validation. It's actually kind of bizarre, but it's a useful trick, and for both that and for kernels, just use this as your value. Okay. That's all I want to say for now about explicit features, because chances are in most data science you won't do this. You will actually just use a nonlinear classifier directly, like a kernel-based classifier, or like a gradient-boosted decision tree. But it's useful to know a little bit about this, especially in the context of kernels, because kernels actually are doing exactly these things, just in a slightly different way. So with that being said, let me very briefly talk about kernels, because this is really kernels, while they are currently, I guess I should say, while kernels are kind of currently out of favor, they've fallen out of favor and in favor of deep learning methods, I guess, broadly speaking, in machine learning. They really are one of the most important advances in machine learning over the past 20 years, maybe more like 25 years now. And they're still the best performing approach, or the simplest approach, for a lot of medium-sized problems. Okay, so what is a kernel function? And you actually are even doing some of that in your homework, probably without really knowing what they are even, which is fine. But they're a really nice way of capturing nonlinear functions of your underlying data. Now, kernels fundamentally are about a very particular, when someone says kernel, they're using a kernel method in machine learning. All they mean is the following. They just mean that they are using a very specific type of hypothesis class defined in the following way. Remember, different methods mean different specifying a loss or the hypothesis or anything else a certain way. Just like a neural network is a certain kind of hypothesis function, a kernel method is a kind of hypothesis function. In particular, the kernel hypothesis is just the hypothesis of x equals the sum from I equals 1 to m of theta I and the kernel between x and xi. All right, where k is what's called a kernel function. That maps, I think I'm back now to talking about x as being, yeah, I'm back away from my feature notation, so I'm back with x being n-dimensional. But it maps from the two inputs to real numbers. And there are some conditions on that function k, but for now you don't have to worry about any of those. Okay, that's all a kernel function actually is. Or sorry, all the kernel hypothesis actually is. And oftentimes you see it sort of, people will talk about like these things like Hilbert spaces and reproducing kernel Hilbert spaces, stuff like this. That's all nice math, and the math is very cool behind all of it. But fundamentally, what it all comes down to is just this thing. Now, there are a few important points here, which I'll highlight actually more later also. But just to mention briefly, this number here is the number of samples you have. Okay, so we now have a number of parameters, theta, which is actually always equal to our number of samples. So if m and n weren't confusing enough to you before, now they're actually the same in some sense, is that our size of our parameters are always the same as the number of examples. I guess not the same as our input size anymore. This means a couple things, though. First of all, it means that to compute this hypothesis function, I have to keep around all my data, because I actually have to compute this function between, I'll show some examples in a second, between my point I'm evaluating on and my examples that I have in my data set. And it also means the number of parameters I have grows with my data set size. Okay? So those are important points to mention, but we'll get back to that in a second. So what's really cool about kernels, and this is why I actually won't prove this here, because it takes a few slides. I mean, a few slides to prove, and I'll try to go through it, put up some descriptions in the notes over the break. But what kernels do is that kernels can actually implicitly represent high-dimensional features. So, d-degree polynomials for large inputs. That would be that n plus d choose n, or before we had k plus d choose k. It can represent classifiers exactly as if you used high-dimensional features, but without actually creating the features themselves, by doing it implicitly. It's not that hard to show, but it is maybe half a lecture worth. So I'm actually not going to cover that here, but I will put up some notes on that over the break. Okay, so here's the two most common examples of kernels you will see: the polynomial kernel, which is two inputs now. Actually, I'm calling x and z just to keep them distinct. I take 1 plus x transpose z, just the inner product there, and raise that whole thing to the dth power. Okay, looks simple enough. All right, and I'm telling you without any proof whatsoever, but just I'm telling you that if you use this hypothesis function with this kernel, that is exactly the same in terms of the representational capacity of the classifier as if you use the full n plus d choose d dimensional polynomial features over your raw inputs. So that the classifier itself are identical. Classifiers themselves are identical in both cases. Okay, that's kind of interesting, right? Seems odd, but that one actually isn't that hard to prove. That one, it takes a few lines, but it's again, more than we're going to go through here. Even more crazy, let's look at the RBF kernel. So that's sort of this thing here where I have k between x and z is just kind of like x was one of them was a center, but these are two input points, remember, not any centers. I'm not defining any centers here. I'm just taking this kernel to be the difference between these 2 points. It turns out this is actually exactly equivalent to if you used an infinite dimensional RBF feature with a center around every single point that there exists in the space. Okay? So this is now an infinite, not just a big feature, but actually an infinite dimensional feature that you cannot represent actually. Again, that seems kind of interesting. Seems hard to understand why that might be the case. It falls out of sort of an integral type formula. If you're curious, you can integrate to get this result. But this is a really nice thing, because now we don't even have to worry about picking our centers or anything like that. We actually can have a dense covering of all centers in all our space while not actually representing it ever by just using these kernel functions. So this is why these properties, by the way, are why for 15 years or so, kernels were the absolute hottest topic in machine learning before deep learning came along and kind of pushed them to the back burner, at least we'll say. But if you have and by the way, if I think you guys are actually using these things a little bit in your one of your homework assignments, where you actually can specify to support vector machine which kernel you want to use. You can be linear, which is just a linear classifier, or it can be a polynomial or a RBF kernel, and you can sort of play around with each of them. Okay, so that sounds kind of incredible, and it is kind of a little incredible at first. Yeah, question. Right, so the question is, what is Z in this thing? Z is just, X and Z are just two different inputs. I'm just writing it this way so that I don't have to have XI and XJ or something like that. I could just written like XI and XJ, but then the inner product gets a little nasty. They're just two different inputs. Yeah. You always run the kernel basically between some input to the function X and some other data point here. And so those are just two data points. Yeah. But again, this is not like an approximation or anything like that. This is saying exactly, if I use that hypothesis function and these kernels, I'm actually representing it as if, mathematically equivalent to using the full polynomial feature here. Oops, I skipped the wrong one. Using the full polynomial feature there, or using the full, really infinite radial basis function feature within every point in space. So that's a pretty nice property. And honestly, at some point, you have to sort of ask yourself, like, kind of what's the catch? Why aren't everyone, that seems kind of amazing. Why doesn't everyone just use kernels for everything? So there's a problem here. So look at this hypothesis function again, right? And I want to emphasize this again now. The number of parameters we have in linear regression, for example, did not originally, right? It was independent of the number of data points we had. So we could keep adding more and more data. We would still just have a fixed number of features, right? And a fixed number of parameters in our model. With a model like this, all of a sudden now, every new data point I add, I'm adding another feature another parameter to my model. This is something called a non-parametric method. By the way, non-parametric is kind of a weird term. There are parameters. It's just that the number of parameters grows with the size of the data. That's actually what's called a non-parametric algorithm. And the sort of practical result here is that most machine learning algorithms end up now having complexity something like m squared. It's the number of data points you have squared. And this really can kill you if you have large data sets. So while kernels were really kind of this breakthrough in representational power, they weren't sort of the most natural fit for really, really big data sets. And what's happened in recent years is that people have realized that when you have really, really big data sets, you are better off with some large but still fixed capacity model like a big neural network, and just that does not grow with the number of data points, so you can still run with however many data points you want, rather than use something like a kernel, which scales usually quadratically or worse in the number of total data points. There are ways around this, and actually people here have worked on ways to approximate this with sampling, and you can get at some very sort of nice methods for doing that, but ultimately this does seem to be a downside to a lot of these methods. That they just don't have the representational capacity that you want when you have to limit them to not being overly complex. Okay, so with that being said, let's look at one of those cases. So poll number 2. So if we have this function and an RBF kernel, what is the complexity of computing the gradient for the machine learning objective here? It's actually independent of what the actual loss is, I'm telling you. I have my objective here, right? I want to minimize the sum of losses between my data points and their corresponding output. The way I minimize that in practice is I compute the gradient of this thing, and then I take a small step in the parameters in that direction. So let's assume we're using the RBF kernel. this particular parameterization, what's the complexity of computing those things? Just one gradient, I should say, right? What's the complexity of computing one gradient with this guy here? Now you guys are sick of complexity polls. I think this is the last one for a while, but these are the things that come to my mind, at least when I think about. Okay, so what did people say? All right, so a pretty even split among these first three ones, actually. Who wants to chime in on which one they think is the correct? I'm going to keep asking this, so someone has to answer. Yes.
M squared n because there are m parameters.
Okay.
In the kernel itself, you need to sum over all n samples.
Okay.
Each with n.
Okay. I think that anyone else want to argue anything for the other ones? Okay, so everyone was again convinced fully by that argument. Okay, so that is correct. Let me show one way of seeing that, and actually one way of seeing that is to actually ignore gradients entirely. We don't actually even need the gradient to show this. So if we have, remember, I'm computing. Let's just compute the objective, right? So I'm computing the sum from I equals 1 to m of the loss between h of xi and yi, right? So that this I have to go through this loop m different times, and this thing here also requires a loop of m over m things. So I'll write it with a different sum, but this basically is going to be the sum from j equals 1 to m of theta j between times the kernel of xi and xj. In other words, I need to compute all possible kernels, xi, xj, for all combinations of examples. And then this term here will involve, this is going to be order n, because it will involve a sum over the dimension, right? So you have two loops of size m, one loop of size n. If you're doing the gradient, everything stays the same. You just basically have to accumulate the actual kernel functions themselves, not just their sum of them. You know, rather than just summing them together, you have to, if you just look at the partial derivatives, you'll find that you have to just basically compute a vector that accumulates these different things together. But basically, you have the same thing: is that you have to loop over all your samples and then loop over all your you have to loop over your samples and compute the hypothesis function, and then for each of those, you have to compute the hypothesis function. You have to loop over all your samples again. So you have this double loop over all your samples, and this, by the way, is for a single iteration of gradient descent, right? So to compute a single update of gradient descent with a kernel, you need to talk about m squared computation, which is exactly why these things are tricky in practice. There are ways to sort of approximate this with less, but then you're back in the regime of something very much like just fixed features again. So it's sort of, these seem magical, but you do pay a price for this sort of magic of being able to work with these implicit feature spaces that seem so great. Okay. The last thing I want to sort of mention in this set of slides is just going through some examples of classification. I'm actually not going to belabor this point here because mainly it's just sort of looking at examples of nonlinear classifiers. So when you see one, you sort of see them all. But we'll show one, and then we'll kind of go from there. And I'll breeze through the rest, and you can look at them kind of on your own, and then also go through the notes, generate them in the notes yourself. Okay, so again, one of the nice things about our whole architecture, which I really emphasized many times now, is that when we switch, because we're setting up classification and regression in the same way, we could get the same, we get nonlinear classification just as easily as we got nonlinear regression. And so in particular, if we have a classification problem like the SVM, remember the SVM is we're minimizing a sum of hinge losses plus a regularization term on the parameters. That was the support vector machine objective we had. The only difference now when we go to the nonlinear case is that now X contains nonlinear features of the input instead of the raw inputs themselves. Everything else remains exactly the same, and you just get nonlinear classification. So this is our kind of picture we had in our minds before about how do you actually classify data like the malignant versus the benign tumors in our example with a linear classifier. This region here was all the positively labeled examples. This region here was a negatively labeled examples, and this is the separating line between them. So everything on this side is positive, is predicted to be positive. This side is predicted to be negative. Of course, we're not getting 0% error here because there are some mistakes you can make, but there's actually no classifier which gets 0% error here. No linear classifier, sorry. So we can do the same thing with nonlinear classifiers. So again, rather than having a linear classifier here, we just plug in the nonlinear features, say a squared feature here and a squared feature there, being sure to normalize beforehand because you don't want to not do that. But here would be a decision boundary for 2-degree polynomial features. So we now have a nice kind of curved boundary here that actually does capture maybe a little bit more accurately what you kind of expect that to look like. And we can keep doing this, right? We can go degree 3 and degree 10. And just like you saw overfitting in the case of polynomials for regression, you'll get similar overfitting things here, right? So again, remember, degree 10 is actually a fair number of features because it's 12 choose 2 different features here. Because you can have products of all of one up to the power d and all the other up to the power d. But you get the same kind of overfitting as you can for the case of linear regression, and all the same caveats of regularization. These things also apply for nonlinear classification. The same kind of thing happens with RBFs. So here we're going to show a couple of different RBFs. Here would be RBFs with I think 3 RBFs over the space, a certain selection for the bandwidth. Here's, if you have a lot more RBFs over each dimension, you can get this overfitting. Really, there's actually 3 ways to, and here's even more RBFs over the whole thing, and you can start to really see how you overfit. Basically, I'm classifying this whole region here, but like having little pockets of other things there and little pockets of red there, et cetera. So I'm starting to overfit my data pretty heavily here. As a last sort of note, there's 3 ways we can, for RBFs, there's 3 ways we can control model complexity. The number of RBF centers, right? This or the number of points, the regularization, which we've talked about before, and then the bandwidth. And by doing each of those, and there's some examples here, but mainly it's just sort of illustrating different degrees of overfitting, et cetera. You can kind of control that overfitting or not. So this is, different bandwidth parameters. This one's a pretty narrow bandwidth. This is a medium bandwidth. This is the bandwidth. A lower bandwidth is actually the one chosen by the median trick, and so it looks kind of like one of the better fits to this data. Now, I think you can actually kind of argue whether or not this is really a nonlinear data set. You might say, look, it's pretty much just linear here. There isn't much you can do with this particular representation. But in general, of course, you can have separators that really are nonlinear. Okay, so that's actually all I want to say about nonlinear features, because while it's useful to know about all these things, the reality is, for the most part, you will sort of use a baked-in classifier like a support vector machine with a nonlinear feature or a nonlinear kernel or a boosted decision tree that gives you these nonlinearities, but where you don't have to worry about them explicitly. So on the flip side, though, it is important to sort of remember that these notions of regularization and model complexity apply to any nonlinear classifier. So whenever you're just trying to solve a problem with some nonlinear modeling technique, you'll need to know about things like regularization and model complexity and overfitting. Okay, so with that being said, the last thing I'm going to talk about today is the notion of evaluating machine learning models. And actually, this is probably one of the most useful and practical things you can actually, this set of 10 notes, or 10 slides or so, is one of the most practical parts of the course, actually. There's only a few of these. So I'm going to talk about 2 things, really. I'm going to talk about, first, generally evaluating machine learning algorithms, and then secondly, I'm going to talk about some ways of evaluating classification in particular that's a little bit different from what we've seen so far, but which are very common in practice. Okay, so let me get started with the following sort of setting. So a common strategy for evaluating algorithms is the following. So I wanted to now, report in my paper how well a support vector machine works on this particular task. What I'm going to do is I'm going to first divide my data set into a training and a holdout set, as we were taught to. I'm going to try different algorithms, or maybe a signal algorithm with different hyperparameters. Using that training set, I'm going to train it with the training set. And then I'm going to evaluate the performance on the holdout set and report the best one, because that's the one I want to report as my result. Okay, so what's wrong with that procedure? Everything seems fine, right? I'm using a holdout set to evaluate performance. What could possibly go wrong? Yeah. Okay, that's one possibility. I was actually something more fundamental, I think, than that, even. Any other thoughts? Yeah. Yes, that's the main thing I actually want to emphasize here. That's exactly right. So what he said was we are overfitting our hyperparameters to our holdout set. So consider the following classifier. It just predicts randomly. The hyperparameter is a random number generator. Training does not actually use the data at all. It just predicts, based upon its random number generator, a bunch of labels on the holdout set. Okay, I could tune the random number generator to a point where I get 0 error on my holdout set. And I have learned nothing here, of course, right? All I am doing is I'm just memorizing my holdout set instead of my training set. I'm overfitting in the exact same way I overfit before on the training set. I'm just doing it on the holdout set instead. So you cannot do this. And this procedure is wrong. It's not just about bias in the data set. It's about fundamentally, I am falling into the same trap I fell into before here. So this is actually incredibly important in data science in particular, because you will want to describe the performance of your actual algorithm. What you really think the true underlying performance is. And if you do it this way, this will be a unfair and incorrect, scientifically wrong estimate of your true performance. So what you really need to, so this is the issues with the previous is they were effectively fitting hyperparameters to the holdout set. And I gave you this example of an algorithm that ignores the training set entirely, and given a large enough hyperparameter search, we can get perfect holdout performance. Okay, so here's what you do instead. What you do instead is you bring back this notion of this test set, which I tried to avoid all mention of, but now I finally can actually call this a test set. Okay, so here's what I do. I divide my data not just one time, but actually not just one time, but actually 2 times. First, I take all my data and I split off some of it as a test set, and I hide that away forever. Not forever, but almost forever. I put it away at the beginning of all my experiments. I never open up and never look at that box again. Then what I do is I take the rest of my data and divide that into a training set and a holdout or validation set. Maybe like 50% and 20%, right? All these numbers are approximate here. I train my learning algorithm to learn the parameters of the training set, and I use my holdout set to find hyperparameters. Okay, and I do that until I've found what I'm convinced are the best set of hyperparameters for this data. I can then optionally retrain the entire system on both of those, because I can use all that I want to. And then one last time before I release my results, I look at the performance of this whole thing on the test set. And if the results are bad, I put away this problem forever and never look at it again, because I know my true results are actually bad. And if they're good, so basically I report the results no matter what. If they're bad, I just ignore them entirely and work on something else completely new. And if they're good, I publish the paper and get lots of credit for that. There's a question there. Okay, so the question is, why is the test set bigger than the holdout set? These are all just sort of approximations and numbers here to get sort of, they're all just approximations. The 70-30 is a common thing. And then once you have this inner one here, this is approximately 70-32 of what's left. Don't read too much into those numbers. They will vary a lot depending on how much data you have. Okay, so the problem here is that no one would ever do this in practice, right? No one would ever spend months tuning hyperparameters and fitting algorithms, look at one evaluation on a test set. If it wasn't good, throw away all their work and never touch the problem again. Even though that's what you really should do from a standpoint of statistical accuracy. So in practice, what you do is you try to sort of peak as little as you can, but you peak sometimes, right? Sometimes you sort of say, okay, I'm pretty confident now I have a good system. Let me just see what it is. And no, it's not that good yet. So let me try something else, right? And I'll peak again a couple times, and I'll sort of repeat this process a few times. And by the end, you have the same issue. If you're really lucky, maybe you can collect more data, and every time you peak, you really do throw away the test set, and you generate a brand new set. That would be an ideal way of doing it. But oftentimes you really can't do that, right? So you oftentimes do, and we're all guilty of this, or at least I know I am guilty of this. You do peak at the test set a few times. And while you hope this does not completely invalidate your results, we're not doing things like fitting random seeds to the test set, it does in some sense sort of subtly bias your selection of algorithms and other things toward this particular test set. There's actually I think a good argument to be made that a lot of contests in data science are actually kind of overfitting to test sets, or a lot of benchmarks at this point are being overfit to the test set. So this is true, in research as well as data science practice. So if you're trying to establish some effect for some application you're working on as a data scientist, you will probably do this. You'll probably have a test set that you use to report your performance, and you will probably, before you put this number in your slides, you will check what that number actually is before you do that, right? And you will improve that number to get as good results as you can. So the reality is you have to be aware of this and be aware that you're doing this. So again, I don't think it's right to try to avoid this entirely. I think it's unrealistic. But I think it's important to keep a few caveats in mind. Realize what you're doing as you're doing this. Realize that you are actually overfitting your test set to a certain extent, or you're fitting your test set, and try the following techniques to kind of avoid it. So the first one is evaluate your system. If you're developing some data science pipeline that's actually going to be applied to real new data in the wild, try as much as possible to simulate what the experience would be of actually running that system in the wild, right? On new data that's coming in some streaming system, figure out how you would experience examples as you really would in deployment, and evaluate how your system actually will behave under that example, under that setting, right? Do that as often as possible. If you do suspect, if you've checked just too many times and you're just confident, okay, I know I'm overfitting to my test set, see if you can recollect the data, right? See if you can recollect a new sample of test data that is not going to be biased by your old decisions there. And you're going to do this. You're going to peek sometimes behind the curtain, but do it as little as possible, and be aware that every time you do it, you slightly invalidate your results. If you're careful about that and aren't too blatant about this, chances are you will actually be okay. And when you really have the ultimate test of your system, which is when you deploy it on brand new data and really need to have it work in practice, things will hopefully be okay. I should mention there's actually a really cool area of research called adaptive data analysis, which uses techniques from differential privacy to actually guarantee that no overfitting is happening to a test set. That is very much a research area right now. It is not a actual technology yet, but there are some cool techniques people are thinking about, at least, to avoid this from a more theoretical perspective. Okay, the last thing I want to say here, and I want to kind of get through this quickly. So I have 6 more slides, so we'll see what I can do. 1 minute each. What I want to emphasize here is that although for regression tasks, for the most part, the way you evaluate them is the same as what you train on. You might use like an absolute loss instead of a squared loss to evaluate things, but it's sort of, typically just do that. I'm evaluating element by element and see how it works. But classification is a little different. Oftentimes you have very different methods for evaluating the performance of classifiers. And so I want to emphasize, just mention a few of these methods here, because these are also extremely common in practice. The reason is that oftentimes there's very different costs associated with different types of classifications. So if I call a benign tumor malignant versus calling a malignant tumor benign, those are both just errors according to 0-1 loss, right? They're both just a mistake. But there's very different costs associated with them in the real world, right? And those mean very different things. One's this called type 1 and type 2 errors or things like this, but they're very different things. And so we need to think of them differently than we do in terms of just regression predictions being off or on. And we should think about them differently than we do in terms of 0-1 loss. And so for binary classes, at least, and this is probably something you've likely seen before, if there's a whole sort of matrix of possible outcomes here, right? The actual class can be positive. I predict positive. That's called a true positive. That's good. I'm correctly identifying a malignant tumor. And by the way, these are not symmetric. So there has to be a notion of what the positive class versus the negative class here is. So those are different things here. And oftentimes that's sort of inherent in the data. You think of the positive class as being calling a tumor malignant is the positive example. And but you need to define kind of what that is for each class or for each problem. So I can predict it to be positive, or it can be actually negative, and I call it positive. And that's called a false positive. All right, so a tumor is actually benign. I call it malignant. There's a cost associated with that. You have to do further tests, or maybe in the worst case, actual procedure on someone that's unnecessary. If a tumor is actually positive and I call it negative, that's false negative. This means that I could fail to detect cancer that has other costs associated with it. I don't know which one's worse, honestly, but they're very different, those two settings, right? And 0-1 loss treats them the same way, and they should not be treated the same way. You have to understand the difference between them and report the difference between them in a reasonable way. This is also very important when you have very imbalanced data sets. So we sort of had a synthetic example where there's a reasonably even number of malignant and benign tumors. That's probably not the case in reality. In the reality, a lot of tests or systems you really develop have a very small number of positive examples and a lot of negative examples. And so the ratio of these things is really important in practice. This brings us to sort of a bunch of different metrics we can use to call to define the different quantities that are involved here. So things like true positive rate. That's the number of true positives over the number of true positives plus false negatives. Let's see. I don't want to define all of these. Accuracy is just the number of true positives plus true negatives over all the things. That one's kind of obvious. Precision is actually a little different quantity. It is saying of the things I classified as being positive, so my true positives and false positives, how many were really true positives there? So that's saying that of all my things I predicted to be positive, how many really were positive? Oftentimes those are really important quantities because you only look at the examples you predict to be positive, and I want to know of those things how many were actually positive or not. But all of these are sort of also really important, and they're different. Different things are used, and honestly, different names for these things are used in many different domains. So be aware that all these different combinations exist. And the other thing that comes up with this notion of classification is the notion of changing the prediction threshold. So we've talked so far about we predict whenever the hypothesis is positive, we predict positive. When it's negative, we predict negative. But of course, we could change that threshold too, right? We still believe that things that are more positive, we're more confident in them being really positive or not. So maybe we don't want to predict it's positive unless we're really confident in it or something like that, right? The key idea here is that if we, instead of just treating the hypothesis function as sort of like a something that we, at 0, we switch our class prediction from being true to false, or positive to negative. The key idea is we can actually oftentimes sort all our outputs by their value of hypothesis function and use this to generate kind of interesting metrics. And so this is the last thing I'll say for this time. A lot of nice charts come out of this. So if we take all our examples, for example, and they have different levels of our hypothesis and different actual classes, we can do things like look at, if we don't classify anything, we have 0 false positives but 0 true positives too. If we look at only the first one, we have a true positive rate and say we have 10 total examples. We have a true positive rate of 0.2 because we're getting 0.2 of our examples and 0 false positives. If we look at the first two, I'll have 0.2 true positive rate and 0.2 false positive rate. And I can kind of sweep out this whole space of a number of true positives and a number of false positives that I actually have. If I plot these things against each other, this is called an ROC curve. And so ROC curves show the false positive rate versus the true positive rate of our classifier. If I were in that point there, I'd have a perfect classifier. And if I lie along this line in the middle here, I have a random classifier, essentially. And things like the area under this curve are common metrics for evaluating the performance, especially when you have data sets that are highly unbalanced in classes. There's other things called precision recall curves, which are very similar, but just used in different domains for some subtle reason. But that's actually all I will say right now. So high level again, especially for classification, because there's a difference between the notion of false positives and false negatives and these kind of things, there are different metrics that are very useful to understand the performance classification, which go beyond just the accuracy level of a classifier. You should be aware of those things, and they will likely come up in a lot of domains you sort of focus on. So know about them. But I think we're going to finish that for now and actually going to move on to a very different topic next time, which is sort of basic probability, though we will come back to a little bit more machine learning later in the course. Okay.